Hello, this is Andrew with WMH Racing, and today I am going to go over a little bit how to use the results from testing your motor with the Loadmaster to figure out how you should time the motor. One of the questions I get asked the most about the Loadmaster is, how do we actually use the results? We take and we do this, and what is it that we actually are looking for? Now, if you use one of these motor analyzers and you do it without a load, and you plot on Excel, you take your KV and your current draw and you plot a graph, you can see, well, you're supposed to be able to see the point where the current goes up too much and the RPM doesn't go up, or the KV doesn't go up enough. All right, so we get really big jumps in KV, really big jumps in RPM, but this is still pretty linear. And it is very difficult to actually see where we should be timing the motor based on that information. We go over, and this is with the load on the right side. And we look in this blue line is basically the same plot as the no load. So we get the current, we get the KV, and it's pretty linear. And we look at that and we're like, well, where do we time the motor based on that? So what I have been doing is I have been coming up with a different method to actually figure out where to time the motor. And this method is represented by this orange line. And what we're looking for is the point where this drops down drastically. And as you can see, we get that point right here. And this is where I'm at 42.5 degrees can timing on this motor. Really, we're going to be somewhere between 40 and 42.5. And what I'm actually doing here, this is definitely using the load. So this is using the Loadmaster. What you do is you take and you get all your unloaded values. So your unloaded KV, your unloaded current, and then you do the same thing, and these are for each of the different timing marks on the can. And then you come over here and you do the same thing. You get the loaded values for KV and current. And then we're going to take the difference at each timing mark. We're going to take the difference between the unloaded KV and the loaded KV, and we're going to put those numbers over here. And what we're really looking for is when the difference here jumps. So we can see that our difference here is steadily going up, and it's going to go up, all right, because the system is essentially a brake dyno, and the faster you spin your slave motor, the more load it's going to put on the test motor. So it's going to go up. We expect this difference to go up, but we expect it to maintain some sort of similarity going up. We don't expect it to go massively high until the test motor starts losing power. And so we look at this and we see that it's increasing, and then we get, a decent sized jump from 40 to 42.5, and then a huge jump from 42.5 to 45. The motor is probably going to run more efficient in the 40 to 42.5, but you definitely lose a lot of power from 42.5 to 45. And that is what this is going to be, because basically power is torque times RPM. And this number right here is going to represent a torque value. And it's not going to be an actual torque value, because I can't actually get the true torque number. But this will suffice for a reference. The torque is how fast, how many kV the motor can spin under a load. You see the difference between unloaded and loaded, and how close it can actually get to that loaded or unloaded value is how much torque the motor has. So it will be closer to that value if it has more torque. And this also makes sense because as you go up, the motor loses torque. As you go up in timing, you get less and less torque, right? So this all makes sense. You expect this to increase. And then power is torque times RPM. And we're using kV here and not RPM, which is completely fine because it's going to give us a reference point. Now, the problem you're going to run into when you just specifically do this, you can't just take this number, this reference or this difference, and multiply it by the kV because this number keeps increasing. So if this number keeps increasing and you're multiplying it by a kV that's increasing, you're always going to get a higher number. Instead, we actually have to do the inverse of this number. And the inverse will make it so the closer to a zero difference is the better it is. So the inverse is basically 1 divided by that number, and that creates these numbers in the L column right here. And then we take the numbers in the L column and multiply them by the loaded kV, and we get this number right here in the M column. And this is our power reference. And as you look down, you can see that we go from 15. We have this little bump right here. It goes from 13 and then back up to 14. So it looks like the motor really doesn't want to be timed at 30 degrees on the can either. And we go down, we go down, we go down, and we hit the 42.5 when we've dropped 12.5. Okay. And that's not necessarily bad. This motor would run fine at 42.5, but I wouldn't go past 42.5. Is it past 42.5, we just drop off the face of the earth. And then if we plot those, we can actually see the big fall. And that is all I have today. So thank you for watching.